Okay, good afternoon, everybody. Recording has started. So I graded the quiz 2. The quiz 2 did not go quite as well as quiz 1. I think the average for quiz 1 was something like an 8.3, and the average for the second quiz was lower, more like a 6.3. So a bit of a drop there, which is to be expected because as we go along in chapter 1, the material gets progressively more up to date, I guess. We're kind of just going back all the way through from like high school algebra to pre-calculus. So it's going to continue to scale up a little bit more until we get to chapter 2, which is when we'll actually start learning something which is in the direction of calculus. So this class definitely does have a bit of a scaling up in the first few weeks. So if you didn't do as well on quiz 2 as you thought you were going to do, it might be a good idea for you to attend office hours. Come talk to me and just get a handle on where you're at with the class so that I can recommend you some positive study tips and ideas on how you can do well in the course, because I don't want to see anybody do worse than they thought they were going to do. So that's quiz 2. You'll also notice that the first question on every quiz comes from the extra problems. So theoretically, you guys could be doing these extra problems at home, the ones from the back of each section, just because there have been so many people out from COVID. So just let me know if you need a retake because of something like that. Not a retake, but a reschedule, I guess. All right, any questions about quizzes? I'll hand out the second quiz next class, the graded one. Still have a couple people who need to take it. All right, then let's get started for today. Oh yeah, a couple more announcements actually. So homework 1.6 through 1.9 is due a week from today. So I'm going to try to stick to that deadline. I'll push it back if I have to, but my goal today is to get through the rest of 1.6, 1.7, and start on 1.8. And then on Thursday, I hope to do 1.9 so that you can do all of the homework before the class on Tuesday. That's my goal. If I have to push it back, then I'll push it back, but that's what I'm going to try to do. So don't forget I have office hours today. I've been sort of slowly speeding up the pace at which we're going over material in lecture. So if you start feeling like, wow, this is getting a little bit fast, come to office hours and talk to me, chat with me about the things that I didn't have time to talk as much about as you would have liked, okay? And we will talk that stuff over. I know I sound like a broken record telling everybody to come to office hours, but seriously, that is what is going to save your ass if you're going to try to, overcome. Either you feel like you're not a math person or you're not as well prepared for this class as you thought you were. Coming to office hours is how you're going to save yourself. SI sessions are back in person, I guess. So Monday, 8 to 8:50, Wednesday, Thursday, 6 to 6:50. Highly recommend going to those. Daria, do you have any announcements?
Yeah, just Wednesday and Thursday back in person. Please come. We're going to have some practice for quizzes and homeworks.
All right, great. Any questions administratively before we start? Okay, then let's start. I want to start by reviewing what I was talking about last time. So this is in section 1.6, if you're keeping track on the notes. I think it's in 1.6. Yeah, it's in 1.6. Towards the end, we were talking about converting between exponential forms. So I had to kind of rush through this at the very end of the last lecture, so I want to review what I was talking about here. We have two really common ways of expressing an exponential function. The first way, on the left-hand side, is p naught times a to the power t. We've seen before. That's how I introduced exponential functions to the class originally. Okay, so we have some initial quantity p naught, and as t moves forward, we successively multiply by some growth or decay factor, a. So if a is a number bigger than 1, then each time we multiply p naught times a, if a is bigger than 1, then the number's getting bigger as we go along, okay? The number is getting bigger as we go along. But if a is smaller than 1, okay, then we're going to have a decay value, okay? So let's have a really quick example. If I had something like 5% interest rate, okay, then this tells me that my R value is 0.05, because percent means per 100. So we take 5, divide by 100, and we get 0.05. Okay, so that's our R value. So then we know that our A value, if we have an interest rate, is going to be equal to 1 plus R, which tells us that this is going to be 1.05. And so our equation will be P of t equals P naught times 1.05 to the t. Okay, so as t gets bigger, we multiply, if t is 1, we take our original quantity, multiply by 1.05. If t is 2, we multiply our original quantity times 1.05 times 1.05, and so on and so forth. And you can see how this is going to grow, because if we multiply a number by something which is larger than 1, it's going to grow. Okay? What about if I have not a 5% interest rate, but I have a 5% decay rate? What happens to my R in this circumstance? Still 0.05? Yes. Sorry? That's going to be our A value, but what about our R? Remember, A is equal to 1 plus R. So if your A is 0.95, what was R? Yeah, negative 0.05. Okay, so R is going to be negative, okay, in this circumstance. Negative 0.05. Okay, and then A again is just 1 plus R. 1 plus R. Well, if R is negative 0.05, then what we're really doing is subtracting, right? So then our A value is going to be 0.95, right? So our function will be P of t equals P naught times 0.95 to the t. So in this circumstance, each time t goes up, we multiply by 0.95, right? Which, if we multiply something by a number which is less than 1, the number is going to go down. Okay, so this is just a recap of everything that we've already covered. So let me talk about what the difference is between this way of thinking and then this P naught e to the kt thing. Okay, well, long ago, mathematicians discovered this fabulous number e. And why is it fabulous? Well, it's kind of hard to explain without knowing calculus. But later on, we're going to see why e is so special. It's a number such that if we take the function e to the x, it's its own derivative, which is a really special thing to happen. We don't expect that to happen for many functions. In fact, e to the x is the only function it happens for. So e is a special number, and we often want to express functions in this second form later on, because it's going to be far easier to take derivatives of expressions that look like this than it will be to take derivatives of expressions which look like this. So we want to have this other way of expressing things. And so we just basically say the following. We know that e is a number which is something like 2.714 something something something. Okay, so it's just a number. So if I have a to the t, well, I can rewrite it as e to the kt in the following way. Let me make some more space here. Okay, so if I take P of t equals P naught a to the t, and I want to make another expression, P naught e to the kt, such that these two are equal. Well, I can divide both sides by P naught, and this tells me that a to the t should be equal to e to the kt. And I can rewrite the right-hand side as e to the k to the t. okay? Because if I take a power to a power, I multiply the powers. And then I can take the tth root on both sides. I take the tth root. Now the tth root cancels out the tth power, and I get this equation A is equal to e to the k. So, in the last lecture, we found out how to solve equations like this in order to get k by itself. Can someone tell me what should I do to get k by itself? Hudson? That's right, we take the natural log on both sides. Okay, ln of A is then going to be equal to ln of e to the k. And then what happens on the right-hand side, Hudson?
You take the k down.
Yeah, it's one of our rules. We can either use the most important rule about logs to bring the k in front, or we can also use the fact that ln and e are inverses, right? If I use the second fact, then the right-hand side is nothing but k, right? Okay, so if I have an equation which looks like this, the way I change it into e to the kt is I just take k to be ln of A. Okay, so let's see a quick example of what that looks like. Let's say I have p of t equals 1.05. Why don't we do 3 times 1.05 to the t? And I want to convert to p naught e to the kt. Well, my p naught is just going to be the same as it was before. It's still 3. And then all I'm going to do is use my equation. ln of A is equal to k. So I let k be equal to ln of 1.05. Don't be afraid, this is just a number. Okay, in fact, we can plug it in on our calculator. Let's see what we get. We gotta go sideways for this one. All right, ln of 1.05. Something like 0.04879 dot dot dot. Okay, so my new equation will be p of t is equal to p naught, that's my 3, and then the number e, and now the power is going to become not t, but 0.04879 t. Okay, so this is how I go from p naught a to the t to p naught e to the kt. Any questions about this example that I just did? Okay, I think there's some practice in the homework for you to try these, so that would be good for you to do. There's also a lot of extra problems in this section where you have to switch those things. Okay, so we're going to do a lot of that. All right. So how do I go the other way? Well, the way I go the other way is just by inverting this equation, right? I know that ln of A is equal to k, which all that means is that if I take the exponential on both sides, e to the ln of A is equal to e to the k. And the left-hand side is nothing but a, again, because e and ln are inverses. So this is how I get a. If I know what k is, all I do is I do e to the k, and that tells me what a is going to be. And if I start knowing what a is, the way I figure out k is by doing ln of a. So these are the two ways which we relate these two things. Okay? And the terminology we use here is the following. R is called the growth rate. Sometimes it's called the annual growth rate. If you're talking in terms of years, okay, but it's just the regular growth rate. And k, this special number k, is going to be called the continuous growth rate. okay? The continuous growth rate. All right. Any questions about this so far? All right. The real important stuff in this box is this right here. Okay, this is the most important. Whoa, okay, I don't know why that happened. This is the most important thing in this box, is this relationship. How do I find out what A is if I know what K is? And how do I find out what K is if I know what A is? Okay? That's how you figure it out. Okay? We should also never forget the fact that A is equal to 1 plus R. Okay? So 1 plus R can also come in here if you want to do 1 plus R instead of A. All right, great. Let's do an example in the opposite direction. Say we start with 7 times e to the 0.13t. And I want to convert this to p naught a to the t. Well, what's my p naught going to be?
7.
It's my 7, right? Goes in the same spot for each of them. 7 times e to the something, or 7 times a to the something. Okay, and then I can do one of two things. I can try to solve this algebraically by setting these two things equal to one another, or I can use the formula. Okay, the formula tells me that A is going to be equal to what? E to the k. A is just e to the 0.13. So if you plug that in on your calculator, I don't know what you get. Let's do it. Where's my calculator? Where the hell did my calculator? Oh, there it is. Okay, so let's do e to the power 0.13. Oops, e to the 0.13. We get 1.13882 ... Okay, so that's the way we can do it with the formula. Or we can do it algebraically, right? We just say a to the t equals e to the 0.13 to the t. And we rewrite that right-hand side as e to the 0.13 to the t. And then we take the tth root on both sides. And we get a is equal to e to the 0.13. Okay, so two ways of getting to the same place. You can either just use the formula right away, or you can do the algebra yourself. Any questions on this example here? Yes?
Not really this example, but if we had to do that on a test or on a quiz, and we didn't have a calculator because I don't think we were using them fast, how would we write it out?
Right. Yeah, I wouldn't ask you to give me 1.13882 on the test. I'd ask you a less direct question. I'd ask you maybe like, how can I find the a value if I know what k is, right? Something like that. Something that you can do without a calculator. Yeah, good question. Any other questions on this one? Okay, so let me ask you a quick question here. In this first equation, what is my k value? K equals 0.13. If I were to look at the second equation with A, what would be my R value? Does anybody remember how I find R if I know what A is?
You add 1?
Subtract 1, right? So A is 1.13882. So if I subtract 1 from that, I'm going to get my R, which is 0.13882. what's interesting about these two numbers? They're not the same. Isn't that kind of funny? We have something which we call the continuous growth rate, and it's 0.13. And then we have an equivalent regular growth rate, and it's something different. Okay? So this is going to be a common theme here. Continuous growth rate is not exactly the same as a regular annual growth rate or a regular growth rate. Okay? So that's one thing we have to be a little careful about. We don't want to just take an R value and do e to the RT, because the R doesn't correspond perfectly with the K. We need to use this log relationship. Okay? Any questions about that? No questions? Okay, let's see. We might move on then. You can have some more practice, okay, at this conversion process on problems 8 and problems 9 here, okay? So if this is something that's boggling your mind a little bit, try practicing these ones at home, or come to office hours and we'll practice them together, okay? All right, then there's some additional problems, expanding logs, contracting logs, and some word problems. So I suggest that you try those on your own, because one of them might wind up being a quiz problem for the next quiz. And we're going to move on to section 1.7. Okay, so I'm going to try to get through a bit of material here. So we're actually going to skip this warm-up problem A here. It's a pretty standard exponential problem. This would be a great problem for an exam. Something like this would be a great practice for you. So try it on your own time. And if you have trouble with it, then come talk to me in office hours or send me an email. But we're going to move on and talk about the difference between annual and continuous interest, okay, which is basically what I just talked about. Okay, so this is really just converting between exponential forms, but with money. Okay? So that's literally the only difference here between what we're now going to talk about and what we just talked about. Okay, so before we had that the annual interest rate, R, is the number such that P of t, the amount of money we have after t years, is equal to our original amount of money times 1 plus r to the power t, where t is in years. So from the previous example, we had 5% gave us a value of 1.05, right? And we just multiply that year after year. And this is how compound interest works, normally. So that's annual interest rate. However, we also have something called a continuous interest rate. And when we talk about a continuous interest rate, rather than using the letter R, what letter are we going to use? K. The continuous interest rate K is the number such that P of t is going to be equal to our original amount times e to the power k times t. Okay? And the big takeaway, %5 compounded annually is not the same as 5% compounded continuously. okay? So, banks that want to give you a loan or want to give you a savings account, or you want to start up a brokerage account with Vanguard or something like that, they like to be a little sneaky, okay, and make you think that you're getting a certain interest rate when really they're just compounding your interest rate in a kind of funny way that actually makes it so that you get less than what you're actually getting, right? That's what the bank wants to do. They want to trick you into thinking that you're getting a good deal when really you're not getting a good deal, right? So they have all sorts of different ways of doing this. One of them is to compound interest continuously or not continuously, or to compound interest monthly or something like this. All of this is going to change your effective interest rate. So what you always want to look for if you're doing an account like that is, what is my annual effective rate, okay? The annual effective rate is this R, okay? So if you always just compare based on the same annual effective rate, then you'll be able to tell which account or system or setup is best for you, okay? So let's see an example of how these two things are different. Okay, so let's suppose that $6,000 is going to be deposited into an account paying interest at a nominal rate. Okay, so nominal here, the prefix nom has to do with name, right? That's where the word name comes from, is the Latin prefix nom. So what this really means, okay, when someone says a nominal rate, is in name only. Okay, that's what nominal rate means. Okay, so a nominal rate is the quote-unquote rate which you are going to get. But what you need to then ask is, okay, how is the nominal rate being compounded? Is it being compounded continuously, monthly, annually, biweekly? There are some other ways to compound interest. So this is what you need to ask. So if we have a nominal interest rate of 2.7% compounded annually, then which model are we going to use if we're compounding annually? Huh?
The annual interest?
Yeah, the annual interest one. Who can tell me how I can write it down? P of t is equal to what?
Times
1 plus r to the t. And in the annual circumstance, if we say that there's a nominal interest rate of 2.7% compounded annually, that tells us that the r value is going to be what? 2.7?
No.
No, what's not?
0.27?
Is it 0.27?
0.02? I don't know. 0.027.
Yeah, 0.027 is what we want. I think Adria got that one right. Okay, 0.027, right? We have to take our 2.7 and we have to divide by 100 to get R. Okay, 2.7 we divide by 100. That means move the decimal place over twice. Right? If you move it over once, you get 0.27. If you move it over 2 times, okay, once you get 0.27, 2 times you get 0.027, okay? Great, okay, so find the balance after 5 years. Well, all we have to do is, we should also figure out what P naught is. Well, our original amount, right, is $6,000. So our equation for this problem is going to be $6,000 times 1.027, and they're asking us to find the balance after 5 years. So what we want to do is 6,000 times 1.027. We want to plug in 5, right? We want to do P of 5. So we plug in 1.027 to the 5. Anyone have a calculator on them? Can someone be my dedicated calculator person? I'd really appreciate that. Clayton, you got me? All right. Let's do 6,000 times 1.027 to the 5th. See what we get.
19,823.021.
Like this?
Yeah.
Okay, so $19,000. That seems kind of high. Did you do 1.027?
No, hold on. 6,854.93.
That sounds better. Okay, great. So that's how much money we earn in 5 years if we deposit an investment of $6,000 into this account, earning annual interest. Okay, let's try continuously. Well, if I'm going to use a continuous interest, I should use the continuous model, which of course is e to the kt. And in this case, my p naught's the same. But now, since my nominal rate is 2.7%, I'm going to use that as my continuous interest rate, okay? So in this case, I'm going to let k be equal to 0.027. So I get 6,000 times e to the 0.027 t. So if I plug in 5 in this circumstance, I'm going to get 6,000 times 1.027 to the power 5 times, I'm sorry, this should be e to the power 5 times 0.027. All right, can you plug that one in for me, Clayton?
6,798.89.
Wait a second. Something might have gone wrong here. I think it should probably be more. Let me double check that. Let's see here. 6,000 times e to the 0.027 times 5 and parentheses. I'm getting 6,867.22. 6,000 times e to the 5 times 0.027. Yeah, I'm not sure what went wrong there, but I think this is what we should get for this one. Okay, so we got a slightly different answer in the end, right? After 5 years, in one account I've got $6,867. In the other one I've got $6,854. So you tell me, which is better, continuous interest or annual interest? Continuous. As long as you're the one investing. If you have a loan, which one do you want? Annual interest, right? Because that's going to give you you don't want to pay as much interest, right? All right. So the way to think about it, I guess, is that continuous interest is somewhat more powerful. Okay? Continuous is more powerful. So whether that works for you or against you depends on the nature of the lending, whether you're lending or whether you're getting lent to. All right, great. Any questions about this example here or about continuous interest? Yeah, Brenda?
So if the problem was structured differently in that instead of growing by a certain percentage, it decreased by percentage, would you subtract the growth rate by 1 and use that as your K?
So the question is, if instead of a growth problem, what if we had a decay problem? And is your question, is continuous decay still more powerful than
No.
annual decay, or?
No, I'm
Exactly. So let's say that instead of paying interest, we were deducting money from the account at a nominal rate of 2.7% per year. Under that circumstance, our R value, rather than being 0.027, would be negative 0.027. So we still get A by doing 1 plus R. But because R's negative, it actually decreases the 1. Is that what you were asking?
Somewhat.
So, could you clarify for me what is your question?
It's fine. I guess I'll ask you later.
Okay. Well, is anybody else confused about what it would be like if we were in a situation where it was decreasing rather than increasing?
I guess if
Yeah.
to jump off that, for if it were continuous, it would just be negative 0.027 times t.
Exactly.
Okay.
Yep, it would be negative 0.027 times t. Okay, okay, we should probably see an example of this. Let's find a... Okay, well, actually, this will come back in about 5 minutes, okay? And we'll see an example of what it looks like when it's decreasing, okay? And you just stop me when you get to the point where you get confused on that one, all right? I'll let you know when it's coming up. Okay, so another example you can try at home if you want. Pretty similar stuff, just trying to figure out how to find the amount of time that we need in order to get a certain amount of money, okay? So slightly different type of problem there. All right, so I want to talk now a little bit about something called half-life and doubling time. Okay, so if you've taken a chemistry class, okay, you've probably heard of this thing called a half-life. Someone tell me what is a half-life of a radioactive isotope? Yeah, Annabelle?
Is it how long it takes for half of it to like go away?
Exactly. It's how long it takes for half of it to go away. Okay? So the thing about radioactive isotopes is they decay at a certain rate. So if there's more of a radioactive substance, then more of it is also decaying. It's like this situation that you hear about when you're like, well, Swiss cheese has holes, right? And so if you have more cheese, then you have more holes, and so you have less cheese, right? You ever heard that one before? Yeah. Okay. But that doesn't actually mean that you have less cheese. What it means is that there's a greater percentage, or there's a greater amount of empty space in your cheese. Maybe that's the way to quantify it. Okay, so same kind of deal with half-life. So the half-life of an exponentially decreasing function, or why don't we say quantity, is the time t required for the quantity to be reduced by 50%. Okay, so if I start with a kilogram of carbon 12, then the half-life is the amount of time that it takes for that carbon 12 to decay from 1 kilogram to half a kilogram. Okay, so there's half of it left. In other words, so in terms of math, this means that we want to find the time t such that p of t is equal to what? 1/2 of what we originally had. So 1/2 times p naught. Okay, so that's half-life. And doubling time is exactly the opposite. Doubling time is time t such that the quantity has doubled. So typically doubling time, we were thinking about things that are growing exponentially, like money. We often want to know how much time does it take for me to double my money on an investment. Right? So that's the t such that if I plug it into the p function, I get 2 times what I had originally. 2 times p naught. Okay, any questions about the theory of half-life and doubling time before we see an example? Okay. So, okay, my iPad is being not responsive. Let's see. Here's a good one for decay. Okay. So, we have a can of mountain condensate. Okay, some kind of soda, and it has a certain amount of caffeine in it. Okay, which leaves the body. Okay, leaves the body at a continuous rate of 14% per hour. Okay, which means if I drink a caffeinated beverage like I'm doing right now, in 1 hour, 14% of the caffeine which I consume right now will be gone out of my body, right? And then 1 hour after that, 14% of that remaining amount will also be gone, right? So over time, if I were to graph the amount of caffeine in my body, it's going to look like an exponentially decaying function, right? Because even though 14% of it goes away each hour, it's only 14% of what was still left in my body, okay? So in other words, if I got 1, 2, and 3, the amount of caffeine in my body right here is 14% of what it was, or 14% less than what it was originally. And then at the next point, it's 14% less than what it was the previous hour, and so on and so forth. So the amount of caffeine leaving my body depends on how much caffeine is in my body, okay? If there's lots, then my liver's working overtime, getting rid of it. If there's only a little bit, then it's not being exposed to as much caffeine, and so it's not getting rid of it at the same rate. So let's see what that would look like in terms of an equation. Now we're told that the caffeine is leaving our body at a continuous rate of 14% per hour. So which equation am I going to use? I'm going to use P of t is equal to P naught times e to the kt. Okay, now how about P naught and k? How can I find what they are? Well, P naught is the original amount. What's the original amount in this problem? Yeah, 55 milligrams.
Do you use that formula because it's like continuously equal?
Exactly. I just look for the word continuous in the problem. It says continuous, so I should use the e to the kt method. Okay, how about my k value? Yeah, Annabelle?
0.14.
What do we think about 0.14? Well, let's think about it. 14% per hour. We should take 14 and multiply by 1 over 100. If I do that, I move the decimal place over 2. So 0.14 is right. But there's something that we should consider, which is the fact that this problem is not a growth problem, but a decay problem, right? So how does that change our k value? It should be negative. It's not that we subtract it, although that's in effect what we're going to do. So I think this is coming back to your question, right? What it means if we have a decay problem is that the K value is negative. Okay, that's what it means. Or the R value if you're doing annual interest. Okay, so our K value is actually going to be negative 0.14, okay?
This
So-
might be a dumb question, but why do you say this is a decaying? Because it's leaving your body?
Exactly. So decay means going away, growth means getting more of it, right? If I drank a cup of coffee and the amount of caffeine in my body kept going up forever,
Would it be positive value?
it'd be a growth problem, but also I would die. Yeah. So it's going away. So that's what decay means. It's just going away, and growth means getting larger. Okay. So K is negative 0.14, so, and P naught's 55, so this P of T is going to be equal to 55 times e to the negative 0.14 times t. Okay, great. So that's my formula. And now I want to find the half-life. So I'd like someone to help me come up with an equation that I can write down for the half-life of the caffeine that's going to help me figure out what t value I should use here to get what I want. And then we'll focus on solving it. So how can I write down an equation here that expresses that there's exactly half of my original amount left after a certain amount of time t? Yeah, Hudson?
Could you do, take on the other side of the equation, put 55 times P naught to half, or like divided by 2?
Well, this is my expression for how much of the drug is left in my body, right? After a given amount of time t. Now we're looking for the t value that, when I plug it into this function, what should I get?
The amount left.
I should get the amount left, and how much should I have left? Half of what I had to start with. So I started with 55, so I want to find the time t such that if I plug in 55 times e to the negative 0.14 t, I get half of what I started with, which is 22 and a half, right? No, it's not. It's 27 and a half. Right? That's what I want to find out. Yeah.
You have to use a logarithm here?
Exactly. Jack's way ahead of all of us. He's thinking about logs while we're thinking about setting up equations. Okay, so now we got to use the logarithm to find out what t is, right? So we're going to apply it to both sides. 55 e to the negative 0.14 t on the left-hand side is equal to ln of 27.5 on the right-hand side. Okay, now what?
You take the T down.
Can I take the t down here?
Like move it to the front?
Can I take the t down front? No, why not? Because of the 55. The 55 doesn't have this power on it. Okay, if I had a parentheses here so that the power was on all of this stuff, then yeah, I could go ahead and take it down. But this 55 is causing me trouble. So I might want to take an intermediate step before I move on to something like this to take care of this 55 somehow. And all I have to do is just divide both sides by 55 right when I start. Okay, if I do that, it cancels. Divide by 55 on this side. Then what do I get? I get exactly ln of e to the negative 0.14 t on the left-hand side. And on the right-hand side, I have not ln of 27.5, but I have ln of 1/2. All right, does everybody see why this is a more desirable equation? Because in this circumstance, the 55 is no longer messing me up. I got rid of it. And now I just have ln of e to the negative 0.14